So I'm Alondra Thompson, and my slides look a little different, but it's okay. I help lead the team to develop the data logging system for the on-farm research. I'm a support scientist at the USDA with Harry Schomburg. And so for this presentation, I'm really going to focus more on the development process for the Gateway End-to-End Wireless Data Logging System. Last time I kind of more talked about the system itself, but if you want to learn more about the specifics of the system, we've got videos on the PSA YouTube channel that you should check out. And we've also got some resources on the PSA Google Drive for you. So you can go to the next slide. So I think that our development process is best visualized by an inverted pyramid where each new level builds upon and expands the previous one. So the alpha testing phase can go through multiple iterations, just like ours did. As I'll explain later, we went through 2 major redesigns in 4 years of developing the system. And so it's not always linear. Some of these steps do get repeated. But as we moved along the process, the number of people involved grew, the development of new related technologies kind of grew, the complexity, but also just the usage. And, and the hope, and I think we're getting there, is that we just have, over time, developed a better product that, we're able to record, collect more data, and kind of spur development of new technologies as well. So you can go to the next slide, please. So the first thing we had to do was identify our need. So we identified a stated need and then translated that into the specific design needs and goals for both the firmware and hardware aspects of the system. So it's great to have that kind of general statement, but you really need to break it down to understand what are my goals and how am I going to do it. So next slide, please. So once we identified what we wanted to achieve, we started to figure out how we were going to do it. And it was a small group of people. We worked with, things that we're ordering off online. We built out prototypes of both the hardware and the firmware to kind of provide a proof of concept, maybe also to prove to ourselves that we could do this. And it also just laid the foundation just for the future development of this product, which you'll see it's pretty amazing how far it's come, from all these like hand soldered things. And, I apologize if anybody's having a little bit of PTSD from, looking at these pictures. But it was a lot of work, but, it was simple. And that's what we were able to achieve with just the prototype. You can go to the next slide. Right, so 2017, we got some stuff together. It didn't take long to figure out that hand soldering things was going to take forever. So for the actual deployment, we designed printed circuit boards to lower the build time. And again, this is a point in the process where more people are joining in because we needed more hands-on work to actually, solder, assemble all of these things. So we had 2 groups in Maryland and in North Carolina putting all these things together. And, the first year in the field was pretty rough, but we learned a lot. But we really identified, I think the major lesson from that year was that the gap in our design was that we had no way of knowing whether things were working out, without physically visiting the sites. And some of these sites were more than 4 hours away. And so we lost a lot of data just for the simple fact that we didn't know that there was a problem. So the next slide, please. So 2018 was our first kind of major redesign of the gateway. This is kind of that central router that is getting the data from the field and sending, and now able to send it to the cloud. So with this new feature, it also kind of created the opportunity for the development of a new technology, which was the growers dashboard, because now growers could actually access their data through this dashboard and access the visualizations and explanations of what is happening in their fields. And again, while this worked better than the previous year, there's still a lot of room for improvement. Next slide, please. And that's when Acclima came to our rescue. So engineers at Acclima joined our development team. They're a private company, and they are the designers and manufacturers of the water sensors that we use. And so they brought so much needed expertise, just with the electrical engineering, product design, manufacture. So they really brought a professional aspect to the design. So they took, just the bare bones of our little circuit design, and they made an entirely new product, that still worked the same way, but it was something that could be mass produced and would eventually become commercially available. And again, these were so much better, but we still found areas for improvement. And then that led to our next slide, for I guess starting last year, we formalized our beta testing team. And we were able to do this at this point because our hardware design was pretty much set. We were going to go with this design, and that part wasn't still in development. But what we could develop more was the firmware, but then also the field protocols, and also the other supporting technologies that were going to support this incoming data. So our team included lots of people from multiple collaborators from different backgrounds and with different expertise. And we divided the team into 3 subgroups. And while each group had their own objectives, we also worked together just to optimize not just the system itself, but also the user experience. Because it's like, why would you develop something that's going to be so difficult to use that no one is going to want to use it? So we really needed input from the field team for that. And we needed the data visualization team to be able to support the field team, and then they needed to tell the firmware team what they needed in terms of data formatting. So it was a really synergistic group where we could all work together and bring our own backgrounds to really make this a better product. So next slide. So our first task was just analyzing the system performance during the previous growing season, and analyzing metrics and methods helped us to identify the specific areas for improvement. And again, not just firmware issues, but also hardware issues, but also installation issues. Just having those comparisons of, we've really found out that just those little details can make a big difference. And so we were able to compare and compile all that information and to help us identify the specifics of where we need to improve, not just the system, but also the methods. Next slide. So then we moved into the refinement and optimization phase of our development process. And it was first, we started and during the off season, mostly, at Beltsville. And this is where we were mostly working on firmware issues. And again, firmware was kind of a smaller team, but then as we launched everything into the growing season, we had that whole big team again, where everyone was really, really involved, heavily involved, as we're in real time responding to problems and communicating with one another, understanding what each other's needs are, and just helping each other out in monitoring data, trying to figure out what some of the errors we're seeing are. So there was a lot of communication that really made this team work really well. Yeah, next slide. And now 4 years later, we're approaching product maturity, which is super exciting because it's been a lot of work and a lot of headaches, but also just really exciting to be part of the process of kind of creating something new. And not just for, like Chris was saying, not just for the sake of creating something new, but creating something needed, that was at a price point that we could deploy these things all across our network. And so while we're approaching product maturity, we'll still be monitoring system performance and making updates as needed, but it probably won't be just as heavily involved as before. And we'll also be testing out Clima's redesigned hardware, which is functionally the same as before, but just improved. And they really were an awesome part of our team, and they listened to our feedback about how just the hardware worked out in the field. And so they made design changes as a result of our feedback. And at this point, because we've got, our protocols are pretty much set, we've got, most of our hardware, firmware kind of down, we're able to start really finishing up our documentation and developing training materials that are now available on the PSA shared drive and on the YouTube channel. And so, yeah, it's been a 4-year process, and it wasn't always easy, but just from, Chris threw out that 3 million rows of data, it's just proof that we did something right, and that this is working out, and these data or these development projects are worth the effort. Next slide. And so now you'll hear from a couple of members of our beta testing field team, and they'll give you an idea of what it's like to beta test these things.
Well, thank you, Alondra. I'm sorry I botched your intro there. But I just gonna say, one of the reasons we really wanted to hold up this water example is that story that Alondra just told. We knew we desperately wanted this water data at scale. We felt like so much of the short-term impact of cover crops could be told through the water story, and we just couldn't do that at scale because of the cost. There were other systems available, but the cost was just impossible. And so it's really an exceptional story what you and Harry have been able to accomplish. But again, now is the testimonial time, and Anna is going to give us the down and dirty being a beta tester on the technology like this. So please, thank you, Anna.
Hi, I'm Anna Birnbaum. I'm the field tech at University of Georgia. I've been here since 2019, and Georgia's been involved since the beginning with Julia Gaskin. Chris and Sarah and everyone bravely asked me to give my troubleshooting testimonials today, or beta testing. I think Chris said it very well with his iPhone analogy. When you go into something expecting it to work and then it doesn't work, it's a lot more emotionally draining than going into it expecting to be troubleshooting, and then you get, motivation that now it's working instead of like, oh, now it's not working. So that kind of sums up my experience. I went into kind of thinking it was going to have some issues, but not that many issues, but it kind of turned into being more issues than expected. So that makes it more challenging. So any folks going into beta testing or signing up for beta testing, just go into it expecting things to break, and then, you'll feel more positive about the experience. But I think it's been good that we've done the beta testing amongst many sites with the water sensors, because if they were just testing them out in North Carolina and Maryland, probably less data would have been collected. In some of my photos, you can see we had a lot of issues with water getting into the sensors, which I think is more difficult for this project than it would be if you just had sites at research stations close to your university, where you just drive 15 minutes every day and can check on them. But when you have them at farms 2 hours away and you're making a big day trip out to check on things, it's a lot more difficult, much more. It's a time investment to go see, oh, there's water in that. Oops, I should have brought a backup node. Now I have to go back, get one, replace it. and it just turned into a whole deal. So beta test if you're a very prepared person. Do sites that are closest to you. And what was I gonna say? Oh, and it's good they had it amongst different regions, because say in Georgia, we had 2 tropical storms and I got tons of water in my sensors, but perhaps in Maryland, they had a dry season. So they wouldn't have found this issue if they were just tested up there. I think Kip's on from Alabama. He was gonna say some.
Hello, everyone. My name is Kip Balcom. I'm a research agronomist here in Auburn. I work with ARS, and I agree with everything Anna said. I mean, one of the things when I started this project, I mean, I hate to admit it, I didn't even know I was a beta tester. So, that kind of created some issues right off the bat for me, because I was like, wow, this work. I thought we were already at the end user stage there for a little while. I hate to admit that, but that was true. And so then when I realized, the goal, obviously the beta testing is important. And I think for me, the biggest thing was the travel. Like when we put them out, we put these sensors out, I didn't realize, like I said, that we were really in that testing phase, and I had some that were pretty far away. And so then they would tear up, break, whatever. And, it really was time consuming, trying to take care of that. So if you are interested in beta testing, like Anna said, you want to try to do it somewhat close by, but it is good to have different regions for sure. But try to make it where it's not so hard on you to have to run and check on stuff, because they have this water sensor set up now where at least you can monitor things remotely. You may not necessarily be able to fix it, but at least what's going on. And so that's good. So if you're beta testing one of these other things, you may require trips to the field, whatever. So you just need to take that into consideration. But Stephen talked about some of the documentation. I think that's what this beta testing led to. I mean, they've got really good documentation, and so you can feel good about that. You kind of help contribute to some of that. That's going to make it easier for people down the road. I told him I was going to tell him something about the 7 stages of grief as a beta tester, but I won't do that. Basically you start out sort of in denial, and then you really learn and just take it one day at a time.
I found it's really helpful if you plan your work and travel routes to your farms around bakeries in the countryside, and that really helps with the emotional aspect of beta testing.
Yeah, that's true. I lived in Alabama obviously all my life, and I traveled places I'd never been in Alabama because it's beta testing.
We did bakeries the past 2 years, and now we're starting to do barbecue joints, which is more interesting or a little dicey.
I love that. That has to go into the guide on being a beta tester, plan around bakeries and barbecue. Well, thank you guys. I really appreciate that. I think that I really hope everybody gets that take home message that's considering beta testing. We certainly don't want to scare people off, but we also want people who are really committed to the effort when being in there. And I just have to highlight for both of you guys, you were like just ideal beta testing group. We would get these incredible, we have a system for logging failures so that then we can assign out who's going to tackle and try to diagnose the failure and create the correction. And we would, from both of you, we would get these incredibly detailed, I did this, then I tried this, and then I did that. I mean, it read like a detective story. And they were just so useful for the whole team. So thank you guys again. I think we're ready for the next move on.
Hi, good morning, everyone. My name is Aurelie. For the new member of the teams that don't know me yet, I have been working with PSA for almost 2 years now. So I started as a postdoc in Chris and Steven's lab, and I'm now working as an assistant professor and collaborating with the team. So I wanted to take the time today to tell you more about the water data pipeline. So what we have been doing with the data collected, using the system that Alondra and Harry built and people beta tested. So just a little bit of I have been having different responsibility of the team. So, I help establish the data flow and I help, facilitate communication between members of the modeling team and between other team and the data flow team. And I have been like responsible for that analysis. Brian, next. So before talking about the data pipeline, I wanted to re-emphasize what Stephen and Chris said in their earlier presentation. So when we are, working as part of PSA, so basically the objective of PSA, we want to produce high-level scientific content, but we also want to set an example of how to build a transdisciplinary multi-institution coordinated research network to try to understand the impact of genetic and management and environment and social on like the biological process occurring in the field, so that we can provide recommendations for growers and that we can promote the adoption of more like sustainable practices. So with this being in mind, everything I will present today was designed with the intent to meet several goals. So we wanted to like try to break data silos to facilitate collaborative research. Next. So we wanted to also set standards for data collection and management and demonstrate good management practices. Next. And we wanted to like establish standard for reproducible research. Keep going, Brian. And then we wanted to encourage synergies within the network to try to broaden the impact of what of the analysis we've been conducting. And we wanted to communicate findings, to growers and stakeholders to promote the adoption of conservation practices. Next. So PSA was established in 2015 with like an NRCS CIG grant. And we originally had 3 objectives. So we wanted to try to identify the site-specific drivers of cover crop effect on soil water and nitrogen availability. Next. So we wanted to evaluate the performance of existing process-based hydrological and nitrogen models. And next. And we wanted to deploy tools that demonstrate how timing of cover crop management impacts soil water and nitrogen availability according to local climate, soil properties, growth stage, and species. Okay, keep going. All right. So to be able to meet those objectives, we developed a non-farm network of cover crop adopters. So like Chris and Stephen mentioned, we started in 3 states and continued growing. And with the new grant, we are moving to 23 states involved in the on-farm network. And we have been collecting data for the past 4 growing seasons. And to date, I think we have data in at least 100 different locations, site years. So next. So in each location, we had a very simple experimental design that was ensuring, our ability of like spreading across the network. So we basically established a no cover crop strip within a cover crop field to create 2 adjacent treatments. Next. So yeah, continue. Okay, so in each, no, go back. Oh yeah, no. Okay, so in each site, we collected a bunch of different data. So we collected, sensor data to measure soil water content and soil temperature and some atmospheric parameters. We also collected, management information from the grower. We asked them about, their cover crop planting date and their termination date, their management strategy. And we asked them, about the cash crop they're planting, when they planted it, the soil preparations that they made. And we asked them questions about like fertility. So in addition to that, we collected, weather information using like the federal repository, like Stephen mentioned. We collected information about cover crop biomass, whether it's in field or like decomposing biomass. So we had like information about, quantity and quality. And we collected soil data using either like the Sergo, same as mentioned, Stephen mentioned before, or using like in-field measurement of texture. So when we are collecting this data, we kind of find ourselves with some issue, with 2 different issues. The first problem we had was that those data were collecting separately in each different, by each institution, and we needed to find a solution to bring that data together. The second issue that we were facing was that each of that data was collecting using a different platform or a different source, like for the weather and the soil data. So we had to find a way to to break the data silos between those different institutions and platforms to have one centralized location where we store and manage that data. Next. So to be able to do that, we basically gathered the data into an SQL database where, that facilitated that made the data accessible to all the members of the team. So when the data was in the database, we were finally able to start working on the analysis of that data. Continue. Okay, so based on the objective we had defined in the CIG grant, the analysis initially was oriented in two directions. So we had a nitrogen modeling and a water modeling. So the nitrogen modeling, was was conducted by Resham and Miguel and many other members of the team, and had three objectives. So the first thing they did, they modeled, cover crop residue decomposition and nitrogen release as a function of residue quantity, quality, and climate. Next. Oh yeah, keep going. My animation are not working. Okay, so then they used the result for their model, to validate and improve a process-based model that was already existing, to model nitrogen decomposition. And next. And they try to implement the result from their research, and they're working on it right now, into a decision support tool that will provide nitrogen recommendations to farmers accounting for nitrogen availability from the decomposing cover crop residue. So next, so on the water side, which is the part of the analysis that I have been heavily involved with, we were facing some issues that we have been trying to address from the beginning. So the first thing that we need to realize, like Chris said, we collected millions of rows of data. And the first thing we needed to do is to find a way to automatize the analysis of the data. Because you can't really go through all of that manually, right? So the first step was to try to clean and format the data in a way that we can use it for statistical analysis. Next. So the way the data is being collected right now, we create one time series for each sensor placed in the field. So in each site here, we collect 3 time series. So when you look at the data, and especially on the older data, we had some issue with the system and we had some bad data. So the first step of the process was, to clean the data and remove all the bad values. Keep going. So to do that, we want to establish good data management practices. So the thing we don't want to do is go ahead and delete that data from the database, right? So what we did, we basically added different columns in the database that determine whether or not the data is an outlier, who made that decision, and for what reason. Keep going, Brian. Okay, keep going. So when that was done, we was able, to look at only the data that was not identified as an outlier, which obtained, for that particular site, that particular plot, right? And then we wanted to convert the volumetric water content measurement into an actual depth of water available in the profile, which we thought would be more informative for the growers. So we created an algorithm that basically compute a weighted average of all the data at the different depths and calculate the depth of water. Keep going, Brian. All right, so we obtained for that particular site the following result. So then we were pretty happy. We had clean data. We had an actual value of available water in the profile. So we could go deeper into the processing for the data analysis. So the first thing we did was to try to automatize the identification of infiltration events among the data. So we basically created an algorithm that identifies where infiltration starts and where it ends. Keep going, Brian. So I'm not going to go into detail of what the algorithm actually do, but that's the kind of result we can obtain. So the red dots show the beginning of increase, and the green dots show the end of it. Next slide. So for each one of those infiltration events in all the sensor data, we're able to automatically determine the time of arrival of the water, the amount of water in the profile at the time of arrival. Keep going. And then the time at which we reach the maximum amount of water for that event and the depth of water associated to it. So for example, for that particular rainfall event, it took 9 hours for infiltration to occur, and we had an additional like 5.4 centimeter of water in the profile. Keep going. So from that data, we are also able, to determine what's happening between infiltration events. So we are able to identify drainage and daily uptake and keep going. And if we have a difference, a strong change in the slope of like the uptake, we can also identify the beginning of stress. Keep going. So when we have that done, so when we identify, infiltration events, then we started building the data set for data analysis. Keep going. So the first thing we needed to do was to associate the sensor data to rainfall events. So we gathered all the rainfall information for those sites using the weather API that Stephen mentioned before, developed by Rick in Georgia. And then we identify rainfall event within the rainfall data for all of those sites. And we define the rainfall event as so if it starts raining, and then the rainfall event lasts until all of the water was infiltrated in the soil. And when it rains again, then we're starting, a new infiltration peak. So if you keep going, so for that particular site, every change in color represents, a different rainfall event. And then we created an algorithm that combines the sensor data to the rainfall data, keep going, and associate, one infiltration event to one rainfall event. So if you look at that plot, the data that is in dark blue represent a rainfall event that was associated to a change in water in the sensor data. So in lighter blue, it's a rainfall event that was associated to sensor data, but did not result in an increase in water in the profile. And the gray is just when we don't have any sensor data, right? So keep going. So when we have been able to do that, then we decided that each peak, so each rainfall event that was associated to sensor data, whether or not it resulted in an increase in infiltration, considered one observation that we want to analyze in our analysis. So for example, the first peak in like the cover crop treatment for that particular site is one observation and then another one. And the same rainfall event in the other treatment would constitute like another observation. So then we extracted that information and we were able to build a very long data set that we can send fit into the model. So keep going to the next slide. So for example, the data set would look like something like that. So you would have, like the site in which you are and the treatment and the subplot, and then you would have some information about the rainfall event. So the amount, the duration, the effective intensity, which might not be the same as the overall intensity. And we can talk more about that. But then you have, infiltration, like information about infiltration. And then we added information, about the management practices. So what's the cash crop, what's the number of growing degree days at the time of the rainfall event, the number of species, etc. The termination date. And we also have information about the biomass of the cover crop. And we get that information using the work that Resham has been conducting on the nitrogen side. Keep going. So then so that's pretty much where we are at right now. We have built that data set. And the next step will be to actually go ahead and analyze the data. Keep going. So we are gonna do that in 2 different ways. So the first thing, we're gonna take the on-farm data, keep going. We are gonna take the on-farm data and the nitrogen model, like the output of the nitrogen work. So we fitted all of that in the data cleaning process. We have the secondary data set, keep going. And we are gonna run some descriptive statistic and machine learning techniques to identify, the site-specific drivers of cover crop effect on water availability. So we are gonna be able to say, okay, cover crop biomass is important, or the number of cover crop species is important. We're gonna be able to say, the texture is important, and try to understand, to help us, predict what the cover crop effect is gonna be on water availability, according to like management and soil properties and climate in that location. So then, keep going. We are gonna work with IRS team in Belleville, so with Denis Timlin and David Fleischers and others. And we are gonna take the on-farm data and we are gonna input it into the process-based models they have already built that, you know, take management information and predict water availability and like crop development. We are gonna predict the data we have already collected using these models. We are gonna then keep going. We are gonna take the output of like those predictions, we're gonna feed them into the exact same data cleaning script that I talked about. Keep going. And we are going to do a statistical comparison between the real, like the feature we observe in the real data and the feature we observe in the predicted data to be able to evaluate, you know, the model performance, and one more time, and be able, you know, to validate that model and improve it, and, you know, and do that. So keep going. So when that will be done, we are gonna implement the result, like our finding, into a decision support tool focused on the water. So the idea we have with that is that we want, you know, to bring our result back to the grower, and we want to develop a tool that will use our finding to help farmers better understand how their management practices are impacting water availability in their farm. And the idea will be that if they can understand that, then we can, you know, give them recommendation on how they can improve their management strategies, whether it's like changing cover crop termination timing or changing, you know, the species they are planting to optimize water availability in the field. So the DST will be built using the models that we are, like the statistical and process-based model I've talked about. They will also gather data from our weather API and our Servo API that Stephen mentioned before, and also from the nitrogen DST that Rick and Resham and Miguel are building. Keep going. So then so that would be like trying to, you know, use our result to inform the grower management practices. But then we have been thinking, you know, that we spend a lot of time trying to develop the data cleaning scripts and trying to make sense of the big data we are collecting. And we are thinking that other researchers in the team, but also anywhere in the world, might want to benefit from the work we have been conducted on, like the data processing and making sense of the data. So we are also planning to build a water analysis tool that will basically generalize the data analysis script that we have built, and that will help, you know, any researcher will be able to import their data into our tool and create the exact same data set that I presented earlier. Keep going. And then, you know, so we can use that tool for many different things. We can use it, you know, to promote the research we are doing across the network, but we can also use it to feed real-time visualization, like advanced real-time visualization into the grower dashboard, and also, you know, bring back some information to our participating growers. And keep going one last time. And then all of that is going to fit into a bigger picture where we are going to be able to use, you know, our method and findings to inform like the work that is conducted by other members of the modeling team. So for example, we can, like in the same way that Resham collected data and built some models, and I'm using his output to run as an input to my model, we can imagine that my output will be used by the remote sensing team and the geospatial team to inform their model and create more results that are gonna, you know, broaden the impact of the work we're conducting and answer like more questions. And one last time. So basically, just some final thought on all the information I provided. So our water data pipeline is integrated within our data flow to facilitate the exchange of results and expertise within the team. And next, I also wanted to say that the development of the pipeline I presented today was a step-by-step process and a team effort. And none of that would have been possible without the dedication and patience of our alpha and beta testing teams. So thank you so much, everyone, for the work you have been doing with the water system and the beta testing of the water system. And one last thought is that, next, Brian, that we want to, so that basically is an example of what's possible. Similar work is being conducted, with the nitrogen work and other work. But we also want to encourage other groups within PSA to think about developing similar pipelines that can build on what we have already built, and that can also provide information for new initiatives within the network as new technologies are being developed, tested, and deployed across the network. And that's pretty much everything I wanted to say. And now I will let Resham talk more about the work he has been conducting with the nitrogen data. Thank you.
And Resham, can you give yourself a brief introduction to the team as well?
Hi, this is Resham Thapa. I'm a recent graduate from the University of Maryland with Dr. Stephen Morsky and Kate Tully as my main advisors. And I can proudly say that I'm a recent graduate from the PSA project itself, right? I started working on the very foundation work that this project was built on. And I kind of accomplished some of the work with respect to the decomposition and nitrogen release from various surface cover crop residues, especially in the mid-Atlantic and southeastern US states. So in this picture, you can see that, a very basic picture, from all the farm sites in the very starting of the year of this project built on, right? We have these residue litter bags and the water sensors across this network. So with so many farms enrolled in the project, we have a lot of data coming into our system. So with respect to both the decomposition, nitrogen release, as well as soil water. Next. So the main objective of the PSA project is to build a very suite of different modules that are built or that are refined using the data from these on-farm experiments across the network, so that we can provide better decision-making support for the farmers or extension agent to provide the recommendations to the farmer and facilitate other consumer groups within the network. Next. Ultimately, the models will be used or will be converted into various decision support tools so that farmers or other members in the network can easily communicate with them to get the better or to facilitate the decision making for their particular farms for site-specific management with respect to soil, climate, and management interactions in their farms. Next. So in today's talk, I'll be mostly focused on one of the process-based model that I was heavily working on for the last couple of years. And that model is basically, we are refining the model that University of Georgia, especially I want to thank Dr. Miguel Cabrera and Rick from University of Georgia for this model. So we are trying to refine the existing Synergies model for the surface residue condition, because the model was already working really fine for incorporated residues, but for surface conditions, when residues are left on the surface of the soil, you can see a very great fluctuation in terms of both moisture and temperature in the residue layer. So we need to refine that, or we need to capture that fluctuation in the moisture and temperature to assist a better prediction of the decomposition as well as nitrogen availability from cover crop residues in no-till systems. Next. So this model usually have like certain inputs, very few inputs, so that it can be easily be converted into a decision support tool, right? The first input is a cover crop data in itself, such as the quantity at the time of termination, the quality, such as the nitrogen concentration, or the residue carbon chemistry, which is basically a different carbon pools in the residue, carbohydrate, cellulose, and the lignin content. And we are getting this data by means of destructive sampling in the network right now. And the other thing we need is the initial residue water content. Next. And since we know that the surface residues have an extreme fluctuation in moisture and temperature, and those moisture and temperature drive the decomposition of surface residues, we'll build this residue water potential submodule, which can simulate the diurnal fluctuation in the residue water potential. And this submodule requires very basic inputs that can be easily, we are easily getting this from the weather API that we built. This weather API gets hourly data from commonly available weather data products such as MRMS or the NLDAS2. And using this information, like initial residue water content, the humidity of the year, rainfall, and the air temperature, this module can simulate the hourly fluctuation in the residue water potential. Next. And the final piece of information required is the soil organic carbon, because to get the net N availability from cover crop residues in a particular cropping system, we also need to account for the nitrogen that is mineralized from the organic carbon. Next. So using these inputs, basically you can see here the soil organic carbon data we can get from the Sorgo database. All the weather parameters we need, we are getting from the weather API. So we do not need anybody to collect those information basically, to facilitate this model predictions. The only data it requires now is the cover crop data, which is basically the quantity and the quality at the time of termination. And now using those data inputs, the model can predict the amount of residue decomposing and nitrogen mineralized from cover crop residues in no-till cropping systems. Next. And I just finished this weekend the calibration and validation of this process-based model. And here you can see a simple graph where in the x-axis you can see the modeled fresh organic matter remaining over time, that is the cover crop biomass remaining over time. And on the y-axis you can see the measured biomass remaining over time, which is based upon the litter bag study. So across the network, we have this litter bag studies or the litter bags that were deployed. So you can see a very good relation between the measured values of biomass remaining and the model values of biomass remaining from this model. So both in the calibration dataset as well as in the validation dataset. And this calibration dataset used data from 51 site years. That means 51 different locations, whereas the validation used data from 48 different locations across the mid-Atlantic and southeastern US states. So now with this, we are very much confident that this process-based model, which we have now well calibrated and validated, can be used to provide farmers the recommendation about the residue remaining over time or the persistence of cover crop residues in no-till cropping system. Next. Here, similar graph with respect to nitrogen remaining over time, that is means nitrogen available. So on the y-axis, you can see the measured amount of nitrogen remaining in residues in the litter bags. And in the x-axis, you can see the modeled nitrogen remaining over time from cover crop residues based upon the Synergies model prediction. And again, you can see a very close association between the measured and the model values, both in the calibration as well as the validation data set. And I want to highlight another point that this calibration and validation data set or these sites had a biomass range ranging from as low as 200 kg per hectare all the way up to 10,000 kg per hectare. So the model is performing relatively good for an entire range of biomass in the mid-Atlantic and southeastern US state. So the next step is that as more data is coming out from this residue decomposition work from the mid-Atlantic and the southeastern region, as well as across the nation from the Midwest, we can further refine the calibration of the model, and we can also test this calibrated and validated model using the new data set, how that's going to perform, or how we can refine the model so that we can convert this model into a decision support tools to deploy it across the nation in itself. Next. So basically, from the earlier I showed you that the Synergies model, which is the model I'm working on, this uses 3 data inputs: the Sorgo database, the weather API data, and the cover crop data. And you can see that weather API data and the Sorgo database we are getting from the commonly available or the publicly available data sources. So the only input that this model requires right now is cover crop data, which we get through destructive sampling at the time of termination. Next. So going forward, since we want to automate the whole process, what we want to do is using the proximal sensing using force sensor box or the satellite sensing or the remote sensing approaches, we want to provide the estimates of both the quantity and the quality of cover crop performance across the network or across the farms in farmers' field, so that we can replace the destructive sampling. And these estimates of quantity and quality using both the proximal and remote sensing can then be fed into the Synergies model to get the prediction out of the model. Next. So the first prediction, this is one of the site here from the network. And here you can see the fresh organic matter remaining over time. So the Synergies, the first output of the Synergies model would be prediction of the residue amount remaining over time. And as you know that the quantity of residue on the surface of soil, it will impact not only water dynamics, but also weed dynamics in a particular farm. Because as you have more residues, more water can infiltrate into the system, less runoff from the system. So the cover crop residue can act as a mulch. Next. And this output from the Synergies model will support the water DST that Aurelie is working on, right? And this water DST then can inform the farmers regarding different things like what is the infiltration or the evapotranspiration or the soil water storage benefits that a farmer is achieving through the adoption of cover crops in their particular farm. Next. So the next output is the prediction of nitrogen remaining over time, which is another way of saying that how much nitrogen is available from cover crop residues to the subsequent cash crop. And this will be easily be used to convert, this will be converted into nitrogen management decision support tool that farmers can use to manage the nitrogen for the subsequent cash crop. And once we have this special map of biomass or the cover crop biomass in a particular farm, we can provide the special map of nitrogen availability to the farmers so that farmers can better manage the nitrogen across the entire farm, or also they can be converted into the landscape levels in future modeling. So that's all I have. Thank you.